Welcome back to the class on electrical machines 2. In this lecture, we are going to solve the two numericals on the parallel operation of the alternator. Let me take the first numerical. A 3-phase 11 kilovolt star connected turbo alternator having a synchronous reactance of 6 ohm per phase, negligible resistance, has a armature current of 200 amperes at a unity power factor. When operating at a constant frequency and voltage, the steam emission remains same. The EMF is raised by 25%. Determine the new value of current and power factor of a alternator. In this numerical, the mechanical input to the alternator is constant, whereas we increased the excitation of the alternator so that the induced voltage in an alternator will be raised to the 25%. They ask you to find out what is the new value of current as well as the power factor. The terminal voltage per phase V equal to 11,000 by root 3, we are getting the value 6,350. Synchronous reactance is given 6 ohm. Armature current at a unity power factor is given I 200 amperes. Unity power factor is nothing but a cos pi equal to 1, whereas sin pi equal to 0. The reactance drop at unity power factor that we have taken as I into Xs equal to 206 equal to 1200 volts. So whenever you are not changing the mechanical input, the real power supplied by the alternator is not changing. We increase the field current so that the excitation voltage will be increases. So the reactive current supplied by the alternator will be altered. The EMF generated per phase equal to square root of V square plus IXS whole square. We are getting the 6464 volts. Here, this is the voltage we have taken on the x-axis. The current IR dash we have taken, that is in phase with the voltage. See here, this current equal to I only, because to represent that is supplying only the real power, we have taken the IR dash. This drop is nothing but this vector is nothing but IXS drop, nothing but this quantity. If you find the phasor sum of V and this one, we are getting the excitation voltage E, that is the 6464 volts. Now we changed the excitation so that the EMF induced in alternator is raised by 25%. Supplying a reactive component of the current, that we have taken the Ix dash. The phasor sum of IR dash and Ix dash becomes a I dash, that is nothing but a new value of the current. The angle between the voltage and current that we have taken is phi. Now if you draw the phasor diagram with a new value of the current, this is Ix dash xs, this is perpendicular to the Ix dash, and for this vector we have to add the IR dash xs, nothing but a 1200, already we have calculated this value. Now if we find the phasor sum of V Ix dash xs and IR dash xs, we are getting the new value of the E dash, that is 8080 volts. The new value of the voltage E dash square equal to V plus IA Ix dash xs, nothing but this vector from this point to this point, V plus Ix dash xs whole square plus IR dash xs whole square. The phasor sum of this side and this side gives the E dash, because this is forming the right angle triangle. Now substitute all the values. If you substitute all the values here, because the new value of the voltage is given, the 25% of the old induced voltage, that is 6464. So the new voltage equal to 1.25 into E, we are getting the 8080 volts. Now here this voltage you have to take it as 8080 volts square plus 6350 plus 6 Ix dash whole square plus 200 into 6 whole square. Now you have to find the new value of the reactance current, where if you solve this equation, we are getting the Ix dash equal to 273.33 amperes. So once we know the reactance current and the active current, the phasor sum of these two is nothing but a new value of the current, that is I dash equal to square root of Ix dash square plus IR dash square. Substitute all the values, we are getting the 338.7 amperes. So the new power factor cos pi equal to this current divided by this current. From this phasor diagram, you can see very easily that 0.59 lagging. Now we are going to take up the second numerical. A 3-phase 11 kV 10 megawatts star connected synchronous generator has a synchronous impedance of 0.8 plus j8 ohms per phase. The excitation is such that the DC voltage is 14 kilovolt. Determine the maximum output of the generator, a current and power factor at a maximum power. If the excitation is such that the DC voltage is 14 volts, means this is nothing but excitation voltage, nothing but no load voltage. The per phase voltage V equal to 11,000 by root 3, we are getting the 6,351. The open circuit voltage E equal to, that this is also given the numerical, 14,000 divided by root 3, we are getting the 8,083 volts. The synchronous impedance equal to Zs equal to square root of x square plus Rs square. These values are given the numerical. Substitute all the values. We are getting the 8.04 ohms. The internal angle pi equal to tan inverse xs by Ra. Substitute the xs by Ra value. We are getting the 84.3 degrees. The maximum output of the generator, that is equal to EV by Zs minus V square by Zs cos theta. This is the formula to generate the maximum power developed in a generator. Substitute all the values, we are getting the 5.886 megawatts. Now corresponding to the maximum power, Im equal to square root of E square plus V square minus 2 EV cos theta divided by Zs. Substitute all the values, we are getting the current corresponding to the maximum power, Im equal to 1215 amperes. The power factor equal to the maximum power divided by V into IL. In the numerator, we have taken the per phase power. So in the denominator, we are not taking the root 3, just VL into IL. It gives the 0.763 lakh. Thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of my YouTube channel, so that I am always welcome to answer all your questions.